Welcome to the TUM AI Lecture Series. My name is Florian Bernhard, and it's my great honor to welcome Max Ovsjanikov as our guest speaker today. Max is a professor at computer science at Ecole Polytechnique in Paris, and before that he worked as in the Google image search team. And even before that, Max obtained his PhD from Stanford University under the supervision of Leo Gibas. Max received numerous awards, including an Excellence in Research Award from Stanford, the Eurographics Young Researcher Award, a bronze medal from the CNRS, an ERC Starting Grant, as well as several Best Paper Awards, and many, many more that I won't name now. Max is very well known for his great work on geometric data analysis, and everyone who has at least looked into shape analysis will probably know his pioneering work on functional maps, among many of his other great contributions. I'm looking very much forward to your talk, Max. The stage is yours.
Okay, thank you, Florian, and thank you for the invitation. Thank you for the very kind introduction. I also appreciate everyone who is joining now, especially given that it's SIGGRAPH rebuttal period and the ICCV submission week. So I think, I hope it will be worth your attention. And also, it's a great privilege for me to give this talk. I saw the other speakers in the TUM AI Lecture Series, and I mean, you really have an amazing lineup. So I hope I won't disappoint either. So basically, today I wanted to talk about some progress in kind of the work that we've been doing in the area of shape matching and shape comparison. And this is joint work with many, many people. And I'll mention, of course, papers as I go along. Many of them are my PhD students and also lots of colleagues. So basically, the overall research directions that we've been looking at, and something that I'm interested in for many years now, ever since my PhD, is basically developing tools for computing and analyzing relations across geometric objects. Right, so these could be, for example, point clouds, scans of people in different poses. This could be maybe man-made objects. These could also be some, maybe biological data or even graphs. And hopefully, some of the tools that we develop could be useful across all of these different representations. And so today, I wanted to kind of tell a story of some of the things that we have tried and some of the things that, in retrospect, haven't worked. And some of our maybe more recent discoveries in the shape correspondence problem. And so I wanted to share a little bit this kind of historical context of how we got to where we are, and also describe some of the more exciting developments that we have recently. So basically, I'll talk about shape matching and different ways of formulating the problem. And then I'll talk about spectral techniques for shape correspondence, some kind of learning-based methods with functional maps, and also some recent extensions that I'm particularly excited about. So hopefully I can convey, my enthusiasm to you guys as well. So basically, this is shape correspondence is one of these problems that you can basically describe in a single image, right? And the goal is essentially very, very simple. So I give you a pair of objects like these two shapes, two human shapes, and the goal is to find relations or correspondences between points on these shapes. So for example, you'd like to say that this point on the right arm corresponds to this point on the right arm, etc. So for us as humans, it's kind of a very easy problem, or relatively easy problem to do, especially if you're looking at human shapes, because we come with a lot of semantic knowledge. It gets a little bit harder once you're dealing with more general objects. So for instance, recently we worked with some paleontologists who work on prehistoric humans, and they have interesting data of these scans of jaws of prehistoric humans, and their goal is to find basically relations, so geometric similarity and differences across different objects. And okay, maybe you could find some landmarks, if you kind of know a little bit about anatomy, but already it's kind of tricky to find correspondences between these shapes. And then also we worked with some people in bioinformatics, and they gave us data of RNA molecules. And there, honestly, for me, it's more or less impossible to tell, like, what are the corresponding points. I mean, there's apparently some correspondences you can discover here, but it's very difficult to do just purely by looking at these shapes. Okay, so there are many ways of formulating the problem of shape matching, and like generally once you find these correspondences, there are many things you can do with them. So for instance, you can transfer texture or parametrization, you can transfer segmentation or labels, you can also transfer deformations, which is something that's common in computer graphics, for example, and also other applications like shape interpolation or reconstruction. Something I'm interested in recently is detecting differences or distortion. So for example, in these prehistoric human jaws, that's what you really care about, is finding regions that are similar, but also regions that are dissimilar, and how exactly they're dissimilar. But all of these basically rely on having accurate shape correspondences. So for today, I basically wanted to focus on several key problems. The first one is how do you kind of enable accurate and robust learning on surfaces, specifically for the problem of shape correspondence, but also more broadly, because to me, like shape matching is a nice application, but also learning on surfaces is something that I find interesting in itself. And also a related problem, and I think is something that's a little bit overlooked, is when you're doing learning on surfaces, how do you measure the quality of the map or the correspondence in order to enable accurate learning? So what kinds of losses do you use, for instance? And the general message, kind of jumping ahead a little bit, that I wanted to convey is, first of all, that spectral approaches are useful both for learning and for measuring map quality. And also, I couldn't kind of resist, is that basically geometry is important. So you can try to model shape matching and learning for shape matching as a purely kind of labeling problem, for example, but geometry will come back at some point. So thinking about geometric considerations when you're doing learning turns out to be very important. Okay, so maybe to begin with, and this is kind of the beginning of this historical context for us, is kind of basic non-Euclidean learning, right? So when you're dealing with shapes that are deformable, you cannot apply simple, convolutional neural networks that you would apply, for instance, on images, right? Because if you have like a Euclidean domain, like an image that's represented as a grid, you can define simple convolution. But when you have a shape that is deformable, and if you'd like to apply, for example, convolution in a way that doesn't depend on the pose, then you have to do something different. And there's a set of approaches that especially were pioneered by Michael Bronstein and his colleagues, and were described in this nice survey on geometric deep learning, where basically it's kind of this non-Euclidean learning or intrinsic learning on surfaces, and there's a more recent survey. And the general idea is kind of very simple. So, okay, shapes don't have a Euclidean parametrization, but you can parameterize them locally, right? So if I give you a point X on a surface, then locally I can define basically a patch, and then within this patch I can parameterize it by geodesic distance to X and some direction with respect to some coordinate, like initial like arbitrary reference direction. And so once you have this local parameterization, then basically you can use these kind of polar coordinates to define a local patch, and then you can basically find a trainable kernel, right? So you basically learn a kernel such that when you take a function defined on this patch and you multiply it with this kernel, then you get some kind of result, right? So basically, if you have a kernel that is a 2D patch, and you multiply it with some function on the surface, then basically you get a single scalar value, and then you have values at all points. So you have a function on the surface. And this, what's nice about this formulation is that this kind of, if you're careful about how you define the local parameterization, this is pose invariant, right? And there's a bunch of papers that were introduced in this direction. Now, one thing is that this local parameterization is only defined up to rotation, right? So there's some kind of ambiguity because there's a local reference direction that you have to select in the beginning. And typically, or at least the first approaches that were used were basically to say, okay, we don't know what the reference direction should look like, where it should point. So let's just take basically the response to the product between the function on the surface and this kernel, but across all possible local orientations, right? So you take a max, so it's called angular max pooling, across all possible mappings between this reference direction u in the plane and t of u, which is some direction in the tangent plane. Okay, so this was, this led to one architecture called the Geodesic CNN, which actually shape matching was one of the initial motivations for this architecture. Essentially, it does exactly this. So it takes, these what are called filter banks, just trains some local kernels, and then, tries to apply them in sequence and, do this angular max pooling to resolve this directional ambiguity. So this was a very nice approach and a kind of a big inspiration for us. But if you look at exactly what happens, so there's a problem in how you model shape matching, right? So when you train these filters, you have to basically formulate a loss. Like, how do you train for the optimal correspondence, right? And typically, or at least in this paper, what they did was to say, okay, let's formulate correspondence as a labeling problem, where on some shape X, what I'd like to do is basically predict for every point on this shape, predict basically the vertex ID of the corresponding point on some reference, so like a template, right? And in order to kind of like the loss they use is basically like a logistic regression loss, or it's the same as basically a cross entropy loss, where essentially you say, okay, the prediction of this X is some function, and I'm going to just look at like how much this function correlates at the vertex where X should map, right? So it's basically just saying like, I'm trying to predict vertex IDs, and I only care about at this vertex, how much energy do I have? And okay, so this, I mean, like if you're careful enough with the implementation, you can get these reasonable looking correspondences. So this is the initial shape, and these are some color transfers. But you can actually see there's a problem here. So already there's some discontinuities, and part of the reason is because the loss basically doesn't enforce any continuity. It just says, if I'm wrong at the point where I correspond, then basically it doesn't matter which point I map to, right? So this is one of the reasons for discontinuities. There's actually even a bigger problem, and what happens is it turns out that these kinds of techniques, they often overfit to sampling, to mesh connectivity. So if you're just predicting vertex IDs, then, for example, if you look at the original shapes in the triangulation of the, let's say, like Faust triangulation that some of you might be familiar with, it works well because basically all the shapes have a similar or the same triangulation. But as soon as you try to apply, for example, the same trained network to a new remeshed surface, then you can get some significant error, like a huge error jump, right? So this kinds of approaches they're very nice and they have some good theoretical foundations, but they're quite sensitive to sampling, right? So, this was a question that we asked, like, okay, so these methods are sensitive to sampling, where is the problem, right? Like, can we solve it? So the first problem is the fact that basically when you're doing this mapping, you have this angular max pooling. So every time you map a kernel to a surface, you have to perform this angular max pooling across all possible rotations of how you map the kernel onto the surface. And this basically loses directional information. So maybe the network doesn't have enough expressive power, and it kind of learns something about the local structure, but it doesn't actually learn too much about the geometry. And so we looked into this, and we had this paper in 2018, which is called Multi-directional Geodesic Neural Networks, where essentially the idea was try to, instead of doing this angular max pooling, let's try to keep responses across all orientations of the filter, right? And in order to do that, we had to kind of generalize the notion of a function. And we said, okay, let's, instead of working with real valued functions, let's work with something a little bit more broad. And this was what we call directional functions. These are functions that basically depend on both the point on the domain X, so you have a point, the point, and also some direction in the tangent plane of X, right? So these are basically a function that has two parameters. And then what we showed is that you can define kind of convolution between this kind of directional function and a real valued kernel. And this convolution is basically equivariant, so it doesn't, it doesn't it preserves the ambiguity of the initial orientation, right? So I have a few diagrams of how this works, but I mean this is kind of not the main point of this talk, so I'll maybe skip the technical detail. But this is just to say that basically there are two components to this. So first of all, you need to be able to pull back a directional function on the tangent plane. And the second component is once you do this pullback, you can basically define a notion of convolution that's equivariant, right? So if you're interested, I'll be happy to discuss it, but I mean, these are the two kind of key things that I wanted to convey. And so once you have this basically pullback, then you can define a scalar per point in direction. So like for every orientation of the kernel, you have a scalar, and that gives you a new directional function. And this notion of convolution is basically equivariant. And so we kind of use this architecture, and so we call this multi-directional geodesic neural networks. And we applied standard architecture and used some local parallel transport to do this pullback. And then just to compare to this original geodesic CNN, we modeled shape correspondence as the same with the same problem. So this with this cross entropy loss that I mentioned just a little bit earlier, right? Now, if you look at the results, so basically these are the kinds of results that we got. So first with this geodesic CNN, you see that under remeshing, you get like significant error. Then with our approach, this multi-directional geodesic CNN, we get better correspondences, right? So they're like more accurate. So there was some issue with this loss of orientation that was preventing from accurate modeling. This is just nearest neighbor in descriptor space, so this is kind of a baseline, so it doesn't work well. And here we also plot the correspondence quality. So basically the x-axis is some geodesic error with respect to ground truth, and the y-axis is how like percentage of correspondences that we have below this error. And you see that, so we tried both the original data sets, so we have this Faust and Escape data sets, and we tried both the original data set and also remeshed data set. So the original is in solid lines, and remeshed is in the original is in these dashed lines, and the remeshed is in solid lines. And you can see that, and this is actually something that will come back again and again in my talk, that there are many methods that exist for shape matching, for example, that work super well if you're given perfect data, right? So if you're dealing with Faust data set that is in one-to-one correspondence, then these techniques, they can give you almost a perfect match, right? But the shapes are already almost matched. So, I mean, it's not a difficult problem. But once you change the mesh structure, then these existing techniques like this geodesic CNN, they start failing pretty badly, right? So there's a huge gap. And actually, I mean, our technique is a little bit more robust, but it's still, there is a significant gap between them. Just for comparison, we also tried with PointNet, for example, but the problem is like PointNet is an extrinsic feature extractor, so it doesn't, I mean, it works, it basically fails completely, right? So there is something to be useful, like there's a lot of utility for modeling this as from the point of view of intrinsic surface learning, right? But I think that there's still a lot of, so basically, okay, there's a problem with the loss of directional information, but there's even a bigger problem in terms of like using these kind of, the loss that we use is a cross entropy loss. And secondly, the kinds of like geodesic, for example, so the cross entropy loss does not capture the shape geometry. And also we use this local parallel transport. It's kind of slow and also error prone, right? So what we'd like is to kind of improve upon that. There's another problem that all of these techniques also require training, so ground truth correspondences during training time. So this is, a supervised learning problem. So throughout the rest of the talk, I'll try to kind of convey how we can try to address each of these issues, right? So maybe, the overall question to address here is, can we avoid ground truth maps and compute globally coherent correspondences efficiently, right, with some learning-based techniques? So the thing that we've been excited about for many years now is doing processing in the spectral or Fourier domain. And so I'll show a few techniques that we've developed for solving this problem by basically going to a different domain, right? Okay, so what is this spectral domain? So, I mean, many of you are, especially if you worked a little bit in this area, you probably already know, but just to give it like a 2-slide intro. So, there's something that's very, very powerful on 3D shapes. It's called basically the Laplace-beltrami eigenfunctions. And it's a kind of generalization of the Fourier basis to graphs and surfaces, right? So we have some operator called the Laplacian or the Laplace-beltrami operator. And if you solve the eigenvalue problem with respect to this operator, then so you find these functions phi I and eigenvalues lambda I, then basically these are natural generalizations to the Fourier basis. And they also have many properties that the Fourier basis has. So first of all, they're multi-scale. So there's a kind of notion of like lower frequencies, so smoother functions, and higher frequencies, so more oscillating functions, right? And also given, so there's something called like signal processing on surfaces. So if I give you a function, so like a real valued function, for example, like this function here, you can decompose it as a linear combination of these Laplace-beltrami eigenfunctions. So similar to like a Fourier basis, right? So there's some scalar coefficients times these Laplace-beltrami eigenfunctions, right? And this has turned out to be extremely useful for shape matching. So first of all, because there's a concept that we introduced some years ago called functional maps, which basically uses this idea for shape correspondence. So the idea is, suppose that I have a pair of shapes and I can, have some functions that correspond on these two shapes. If I decompose one function on, let's say, the source shape with respect to its Laplacian basis, and the target shape, again, with respect to its Laplacian basis, and write these coefficients as vectors, then what you can show is that there's always a matrix. So these vectors should always be related by some linear transformation, this matrix C, okay? And this matrix is this functional map matrix. So essentially, this matrix C tells you how to translate coefficients of functions in one basis into coefficients of functions in another basis. And so, if I give you a point-to-point map, what you can do is, there's a closed form expression of how to compute this functional map. Is just basically translating a matrix of a binary matrix representing the correspondence, where every, I have like ij is equal to 1 if and only if I maps to j. So these are maps between vertices. And you can translate it into a matrix between functions as just with this closed form expression. And what's nice is that this functional map matrix is typically much, much smaller than the original correspondence matrix, which has size like number of vertices on the source times number of vertices on the target. And there are also natural constraints that you can put on the correspondence that basically can be expressed as constraints on this matrix C. So as I'll show basically from now on, that this representation allows you to do learning more efficiently and also more accurately. So first, like the basic functional map correspondence pipeline, it looks like this. So suppose I give you a pair of shapes M and N. First, I can compute some k Laplace-beltrami eigenfunctions on the two shapes, store them into matrices, as columns of matrices, and then you can solve the following optimization problem. So I'm looking for a matrix C such that for some descriptors, so these are some pre-computed descriptors, basically this matrix C aligns the descriptors on the source to descriptors on the target. And there's a regularization term that says basically this matrix C should commute with the Laplacian operator. The idea is basically any map that, so we know that this corresponds to preservation of geodesic distances. So this is a kind of regularization on the map. And then once you compute this optimal functional map, you can convert it to a point-to-point map simply by mapping direct delta functions. So it's like a simple post-processing step. So this was, this is the kind of results that you can get if you are careful about both the descriptors that you use and all the parameters, the regularization, etc. And if you're interested in a non-learning approach for this problem, I would recommend maybe taking a look at two recent papers that we have in this direction, and each of them comes with is basically like a recent axiomatic implementation of this functional map-based shape matching without using learning. But the advantage is that you can just download and run it. And we also have a paper that just came out at SIGGRAPH Asia that basically allows you to compute many correspondences when they exist, especially due to symmetries. But this, basically this pipeline, it's kind of, it's simple and efficient, but it assumes that you have some descriptors, right? So it assumes that you're given some approximate descriptors that you expect to correspond. But the problem is if the input descriptors are not in alignment, so if you didn't choose your parameters carefully, then if you do, for example, you perform this pipeline and then you do texture transfer, these are the kinds of results that you would typically get. So you get some very poor texture transfer. So you have lots of distortion, for example, right? So this is not what we want. So now the question is, like in the previous era, you would ask, maybe like to find some better ways to find parameters, you maybe do some optimization, try to find some heuristics. But now we have this powerful tool. So can we basically learn the descriptors so that the correspondences are accurate in the end? So there is an approach that was proposed for this in 2017 called Deep Functional Maps by Orlitani and colleagues. And essentially they used exactly this idea where, you start with some descriptors. So they use the short descriptors, and then they pass it through essentially just some multi-layer perceptrons. So there's like no, there's absolutely no communication between these, between points on the surface. Then you project these descriptors onto the Laplacian basis. You compute the optimal functional map, and you can do this inside the network. Then you can take this functional map, convert it to a soft correspondence, and then impose some loss. So in their case, the loss that they imposed was the following. So this is basically, you have some probability given by the network of point X being matched to point Y, but you also have the ground truth, right? So basically the ground truth for the correspondence of X is some point on the target shape Y. And so you basically penalize this probability by the geodesic distance between the ground truth image of X and the predicted image, the predicted point Y, right? And so the problem, okay, so this is something you can do. The advantage of this approach is that it evaluates the entire map. So instead of evaluating just, like the vertex IDs, how well you're predicting the vertex IDs, it actually evaluates the entire global map in terms of its coherence. And so this basically led to state-of-the-art results in 2017. Now, the problem with this is that you have to store these very large matrices, P, X, and Y. So this is basically a matrix of size, number of vertices on the source by number of vertices on the target. And now, one question that we ask is, like, can we make this loss unsupervised, right? So we know, like, what are some of the good properties that you could expect from a correspondence? And so can we impose those properties in the learning itself, right? And so this led to basically a paper that we had in 2019 at ICCV. And the main idea was basically to follow a similar procedure. So, take, a pair of shapes, pass them through a similar, like, FMNet architecture, compute the functional maps in two directions. So, from shape 1 to shape 2 by solving this optimization, and from shape 2 to shape 1 by solving basically the opposite optimization. And then once we have these two maps, impose some loss on these two maps, and then back propagate this loss to the parameters of the network. So here, I really want to emphasize that this optimization is done inside the network, and it requires you to solve a linear system in the network, which is something you can do basically in TensorFlow directly, right? So this is not some offline step. Okay, so this is this is the general formulation. So we call this SurfMNet. And I should say that there was a parallel paper, basically simultaneous at CVPR the same year, that had a similar formulation, although their loss was quite different. So, I basically will focus on the formulation that we describe. So what are the losses that we use for this paper? So, what we'd like is to kind of promote good quality correspondences and penalize bad correspondences. And so there's some natural constraints that you can have. So for example, we have these two functional maps, one from shape 1 to shape 2, and the second from shape 2 to shape 1. So here we have some kind of cycle consistency. So if you go from 1 to 2 and 2 to 1, we would like to be identity. So we basically impose a loss based on this. It's equivalent in the shape matching domain to bijectivity of the correspondence. We also impose basically these functional maps to be approximately orthonormal. So this corresponds to preserving local areas. We also would like them to basically be near isometric. So we impose commutativity to the Laplacian. And then there's a fourth loss, which is a bit technical, which basically promotes functional maps to be close to point-to-point ones. And what's nice about this formulation is that all of these losses, they only have to deal with basically matrices of very small size. So they're like 30 by 30 matrices. You never have to convert to a large matrix of size, 10,000 by 10,000 if you're dealing with shapes of 10,000 vertices. And so as a result, this is 50 times faster than FMNet to train. So I mean, it's basically like a very significant speed up that you really notice it. So we evaluated this, and what's nice is this was unsupervised method, so we basically didn't use ground truth to train the network, right? We only used it for evaluation, and by the way, I also, if you're interested in like data sets, we kind of assembled a few data sets of remeshed shapes and different kinds of configurations. So if you're interested, I would be happy to share them, because I think that's a much better way to evaluate these kinds of problems. And so, like at the time, it was 2019, we achieved basically state-of-the-art results on both original and remeshed data sets. And also, what's kind of even surprising to me is that we even got better results or comparable results to supervised methods, right? So we compared to many supervised techniques with and without post-processing. And we basically got, results that are, I wouldn't say significantly better, but on par with basically the best supervised methods at the time. And I think what it really shows is that, just having supervision is not good enough, right? Just having ground truth labels is not necessarily the only thing that you need. How you impose the loss and how you train, like how you basically, train your network and how you promote good correspondences is something that's very important as well. So even with unsupervised losses, you can do better or on par to supervised ones, right? Now, so, these are some kind of texture transfer results that you get with this approach. So we have, the source and the ground truth texture transfer, and then we compare different methods, basically both unsupervised. And so this was state-of-the-art at the time. And also supervised methods, like this FMNet, for example, on remeshed shapes, really doesn't work super well, right? So this was, this kind of got us excited because it seemed like, okay, we can do this shape matching by learning good descriptors and use this functional map inside the network. And it seemed like a very powerful technique instead of, for example, doing cross entropy loss on vertex IDs, because that's something that's very sensitive to remeshing. So, so here's just some examples of descriptors that we see before and after optimization. And what's kind of interesting is this network doesn't know anything about the ground truth correspondence, but somehow it still aligns the descriptors based on all of these losses that we use. But the problem is, so in this formulation, we still started with some initial descriptors. So we used the shot, and then we modified the shot descriptors to basically get better correspondences. So the next question that we were wondering about is, can we extract descriptors functions directly from the raw geometry? So, the story was that, okay, it seemed like using this functional map inside the network was a good idea because it allowed us to train fast and accurate correspondences. But we didn't like this this problem that we started with some initial descriptors and we tried to refine them. So the question is, can we basically extract descriptors from the raw 3D geometry? And the second question, which strangely people haven't asked in the past, is how well do these methods generalize across different data sets? So if I train on one data set and apply it to a different data set, even if it's also humans, right? So for example, we have these like scape humans that are in different poses, and we have fast humans that are produced by a different group and also in different poses, but presumably they're all humans. So you should be able to train on one data set and test on the other. So the question is, how well do these existing techniques generalize across different data sets? So here's some failure cases of like methods that use 2000 shapes for training and still fail like quite poorly to generalize. All right. So this basically led to a work that's the CPR 2020, which we call Deep Geometric Functional Maps. And the idea was, okay, instead of extracting descriptors from some predefined features, so like shot, let's take a feature extractor from the original 3D shape. So we use this KP column, which is a kind of a generalization of PointNet++. But let's, instead of predicting vertex IDs, let's still use this functional map extraction layer, right? And here there are basically two contributions. The first one is using this feature extractor from the raw geometry. And the second one is we actually showed how to do regularization inside the network. Right, so this is a work with my PhD students Nicola Donati and Abhishek Sharma, and essentially that was one of the key insights that made it possible that you can solve a linear system not only based on the descriptors, but also based on Laplacian commutativity inside the networks. You can basically backpropagate the solution from the solution of this network back onto the features. Right, so what we call this basically a regularized functional map layer in the network. Right, so I mean, kind of a relatively simple approach, but it seems that it combines two good things. The first one is learning from raw geometry, so it doesn't overfit to the triangulation, for example. And the second one is using this functional map regularization, which means that it can train with small amount of training data. So here, we have some source and ground truth correspondence, and we, applied, like, we took our, trained network and computed the correspondences. And then we also applied some lightweight post-processing, this method called zoom out that works on functional maps. And you can see that especially when you have a small amount of training data, it works particularly better than existing methods. Like 3D coded, for example, was a state-of-the-art method last year. I don't think it's state-of-the-art anymore. So we compared both in terms of accuracy for small training sets and also across different generalizations across different data sets. So what was actually a cool experiment, and I think it's interesting even in other settings, is basically taking, like, training on one data set and then testing on the other and evaluating the accuracy depending on the size of the training set, right? So we compare basically to some state-of-the-art methods, depending on, like, the x-axis is the amount of shapes in the training set, and the y-axis is the average accuracy. So you see that, okay, this approach can get better with, like, more and more data, but there's also a saturation point because it basically doesn't generalize across data sets. There's some kind of inherent bias. And also, it requires, like, thousands of shapes for it to work well. Right? And so, yeah, so these are some, like, results that we got across, generalizing by training on 100 shapes in Serial and testing on this Shrek 2019 remeshed, so basically a collection of different human shapes across different data sets. And interestingly, I would say that, I mean, our method works better than others, but more than that, I would probably say that most methods don't work. I mean, it's just a challenging setting. I mean, I think existing techniques don't generalize super well across training test sets. All right, so this is something to bridge the gap. And now there's still, kind of a problem in this approach, which is that we still use an extrinsic. So we use this regularized functional map layer, but it still uses an extrinsic feature extractor. And to me, it's kind of unsatisfying because we would like to do learning fully in the kind of on the surface in an extrinsic sense. But, so far the techniques that we've tried, I mean, are kind of not very robust. And so the question is, can we enable a robust and efficient intrinsic learning on surfaces? Okay, so that's the question that we wanted to ask in this follow-up work. And basically in the last few minutes, I wanted to describe kind of some of the more recent advances that we've had. So this is a work that we put up on arXiv a few months ago. And basically it has this sort of corny title called Diffusion is All You Need for Learning on Surfaces. And it's a collaboration with people at CMU, so Nick Sharp, Keenan Crane, and a PhD student in my group, Sohaib Ataiki. And basically the idea is, can we find the smallest robust set of components in order to learn on surfaces in an intrinsic way, right? Okay, so what I described in the very beginning of this presentation is this approach that was pioneered by Michael and his colleagues that is based on geodesic convolutions. I mean, there are many different variants of this idea, but they still have a similar flavor. So typically, you have some kind of local parametrization, and so you have this geodesic convolutions, and the other thing that you need is some kind of pooling hierarchies. And both of these kind of building blocks are difficult on surfaces, And it turns out they're both sources of non-robustness. So, things break under changes of triangulation, for example. So what we'd like is to kind of replace them with something simpler and still get good results. And in this work, we basically show that the only thing that you really need is essentially just simulating diffusion on the surface, and more or less that's it. So our approach, or this network that we developed, it basically has three different components. The first one is just standard MLPs. Then there's a learned diffusion layer, and then there's a gradient feature layer. And I'll describe like a little bit why they're necessary without necessarily going into like all the details. But the key, like I think the main thing is just this learned diffusion. I mean, that's I think kind of the main building block. And that's what kind of makes the whole approach robust. And so what is learned diffusion? So basically, just as to give an overview. So what is diffusion to begin with? So diffusion is probably the most well-studied PDE in history. So it's just a process that's defined by this partial differential equation that says that evolution of, for example, heat in time is equal to the Laplacian times the heat at the current moment, right? So if you start with initial source of heat at some point, and you diffuse it after a certain time, it kind of looks like these blurry blobs after basically a certain amount of time, right? I mean, it's very intuitive what happens. And of course, this is something that's well defined on surfaces with differential geometry, and also on meshes with discrete differential geometry or finite element methods, etc. And it's like super well studied on many different domains, including meshes and point cloud and so on. Now, the thing that we wanted to kind of achieve is the following. So typical approaches use convolution and pooling, right? And what we'd like is to replace both of them with something that's simpler and is just diffusion, okay? But the key to make it work is to make the diffusion time a learnable parameter, right? So instead of diffusing for some fixed time, we make the diffusion time t a learnable parameter. And this is a variable that's per channel, so it's not a global single variable. So we make that basically trainable across the network. And so that allows you to kind of find filters that are both local and potentially global, right? Depending on what each filter wants to do, it can make it either very small time or very large time, right? And this is optimized during training. And so, yeah, so what we have is basically a learned diffusion layer that takes some function and produces another function and is parameterized by this diffusion time t that is a trainable parameter, right? And what you can show in this small technical lemma that was actually proved by Nick was that diffusion plus pointwise MLPs can represent all radially symmetric convolutions. So you don't necessarily lose information by going to diffusion instead of doing standard convolution. So now, okay, so this diffusion allows you, plus MLPs allows you to represent radially symmetric convolutions, but in practice, we want also anisotropic filters, right? So not necessarily symmetric filters. So in order to also learn anisotropy, so find filters that are not radially symmetric, we also have this extra component, which we call the spatial gradient features. And essentially, it's very simple. So you start with some real valued function, you compute its gradient. So this is just some vector in the tangent plane. And then we have some learned rotation in the tangent plane, right? So this learned rotation is kind of, okay, how much do you rotate this vector by? And so we then take the inner product between the gradient and this learned rotated gradient, okay? And so this is just something that allows us to learn anisotropic features. And what's important is that this is invariant to the choice of tangent space. So we don't have this problem with the choice of initial orientation because everything is just inner product, right? So now, okay, how do we evaluate diffusion? So there are many different ways of evaluating diffusion. How do we make it trainable? So the thing is that in the Laplacian eigenbases, diffusion simply corresponds to decomposing a function into a set of coefficients, and then multiplying each coefficient with the corresponding exponential times the eigenvalue times the time t, right? So what we do is we basically have some function, input function, we project it onto the Laplacian basis, Then we multiply it by this vector of coefficients where t is a trainable parameter, and then we project back. So the important thing here is that we're not actually doing any learning in the spectral domain. This is just a tool that allows us to basically simulate diffusion while making the time parameter a variable. Of course, there are many alternatives to diffusion, so to this kind of simulation. So for example, you can also do backward Euler, and then you can backpropagate through this linear system. The problem is that this becomes kind of quite large if you're dealing with large meshes, whereas this can be done very efficiently in the reduced spaces. So this is just an efficiency trick, right? But if you don't care about, doing things fast, you actually can do it in this full domain and works even better. Now, so this is the overall architecture. It's very simple. So it works like this. So we have some input features, and then we have basically two things that can happen. We can, so we project it into the spectral basis. We apply some learned diffusion, and this gives us features on the vertices. Then we take the gradient of this function and compute some, rotation of this gradient and inner products. This gives us some features in the tangent space. And then we basically take the inverted gradient and get back our features, right? So essentially, there are only two things that happen. We have MLPs, we have diffusion, and so the standard MLP, and beyond that, we have two things. They have diffusion and gradients, right? That's the only two things that we use. So okay, so what's kind of interesting is that so we don't have any parallel transport. There is no patch parameterization. But this seems to work really well. So for example, we evaluated on different tasks like segmentation of the RNA and also, functional correspondences. So extracting features for functional maps, just like I described earlier. And this basically always produced better results. So for instance, specifically in the case of shape matching, so we compared basically using KP-conv as an extraction layer, as a feature extractor to this diffusion net, and we consistently got better results, both when you train and test on the same data set, and when you train on one data set and you test on another data set. So the average errors are all lower. What was also interesting is that this method, because it's used just based on just diffusion, it's very robust to changes in triangulation because we don't rely on any kind of local patches. And so actually, I think I have some slide about that in just a bit, but it's also extremely fast. So, everything is in a reduced basis. So, with basically, you have like 42 milliseconds per input on 15,000 vertex shapes. And, with even a small amount of memory, you can do some very accurate training because all of the processing typically happens in the reduced basis. And the only things you care about are like either MLPs, which are super fast, or learned diffusion, which in a reduced basis is also extremely fast. And also it runs on meshes and point clouds. So here's some comparisons. So basically, if you we tried in different kinds of meshes, and if you do even basic things like vertex prediction, this technique works well even across different triangulations because we just used like the standard finite element diffusion, and because that has been developed to be invariant under meshing, this kind of we inherit that property. Right? So yeah, we even tried things like training on meshes and testing on point clouds, and training on meshes that are low resolution and testing on very high resolution meshes, and it works basically just as well. Right? So okay, maybe let me skip this. So the last thing, we tried this diffusion with respect to different meshes. It still uses the Laplacian basis. So the last thing I wanted to just very briefly mention, I won't go into detail, is I think it's more like ongoing work, is how do you kind of generalize Laplacian basis to more difficult settings. So for example, when you're dealing with noisy point clouds, so not like clean point clouds where the Laplacian basis doesn't work. Can we go beyond this Fourier basis? And so we had this paper at NeurIPS last year where we basically showed that you can learn both the features and even the basis. So we can kind of generalize beyond the Laplace-beltrami eigenfunction. So it's a little bit involved because you have to train both the basis and then the features separately. But I think the main idea is that it's possible. So that's kind of what got us excited. So, and this approach, because it kind of generalizes the Laplacian basis, it works even on very noisy point clouds. So there's some like kind of challenging examples. We also evaluated on things like these statues with missing parts and clutter, etc., changes of topology. And because we don't rely on the Laplacian basis, it's quite, it's basically a very, very robust method. But I think this is just the first step. And honestly, I think that there's lots of things that still need to be done. And especially like focusing on robustness is something that I think is, we're only now beginning to understand the importance and trying to, get better and better results. Okay. So that's basically all I wanted to mention for today. I know that some of these things were a little bit fast, so hopefully at least, there are a few references. So if you're interested, obviously feel free to reach out or maybe like take a look at the papers. But the main thing I wanted to convey is that these spectral techniques enable basically there are powerful tools for shape matching, both without learning, if you have good features, and with learning, as ways to regularize the networks. And also, these functional map layers that allow you to basically impose losses on the correspondence as a whole, rather than independent point assignments. And so, these recent techniques that I kind of briefly mentioned were, especially the diffusion net and basis learning, allow us to greatly improve the robustness of both the features and even the basis functions. So yeah, thank you very much. I'll be happy to answer any questions.
Okay, thank you very much for this very nice presentation. And I think we can directly get started with the Q&A session. So any questions?
Max, I would have a question to start off. Thank you also from my side for the wonderful presentation. I'm curious, some of the ideas that enter the shape matching are ideas that you typically want, more or less isometries. You want to preserve pairwise distances. You also mentioned preservation of area. Mm-hmm. That, I would say, should limit the applicability to objects which actually exhibit these properties. But how about, in the beginning of your talk, you mentioned sometimes you might want to match a horse to a camel or to a dog or to a cat. And in these cases, you might have drastic variations in pairwise distances or also in area. And have you looked into that? How could one tackle these kinds of problems where shapes are not as, let's say, isometric as the humans?
Yeah, thank you. Yeah, that's a very nice question. And it's true that I didn't get into, I didn't have a chance to really explore the full area. I would say the following. So, for example, imposing these constraints, like preservation of distances or areas, is something that is useful for unsupervised training, right? So where we don't have ground truth. Of course, if we have ground truth, we can also learn, even in the case of non-isometric matching. I don't think that's not a fundamental limitation of any of these approaches. And even functional maps as a representation is something that works well for isometric shape matching, but actually works even more broadly, because for any correspondence, even if it's not isometric, you still have a functional representation. So that's not necessarily a limitation, but the information has to come from somewhere. So if you have ground truth maps for training, you can definitely use them and train a network. And I feel like there's very strong chance that it would work well given enough training. But if you don't have ground truth, if you just have, if you're looking for unsupervised training, then of course you have to be much more clever. And I think some of these constraints or some of these energies I presented, is true that they're more geared towards near isometries. So I would say it's kind of an open question right now, how to do unsupervised training for shapes that are non-isometric. And there, I think it's true that we can do certain things. Like, for example, there's some things that we still would like. For example, having bijectivity is typically a desirable property of a correspondence, right? Having low local distortion, even if you have significant changes in distances, typically you don't want to have entire regions get mapped totally off. So local distortion can also be a good, also continuity is something else that you would like to preserve typically. So just having continuous bijective maps is a very strong signal. I would say that we currently don't have very good tools for doing it in an unsupervised way. So it's definitely something to, that requires more work. So that would be my answer.
So I would have a follow-up question also related to Daniel's question. In general, do you think that functional maps are always the way to go when solving correspondence problems, or do you see there are certain limitations that where you think maybe a different representation or a different paradigm may be more suitable for certain cases? And then also, if there are some limitations, do you think these are like solvable ones in the future, or do you think they're just intrinsic and they cannot be solved for some reason?
That's a very difficult question to answer because I cannot predict the future, so we don't know what's possible, right? Whenever you say something is impossible, there are people working hard to make it possible, right? But I take your point, and so in order, like, maybe to answer the first question, like, do I think functional maps are the best approach for general shape matching? I don't think so, and I don't think it's so. First of all, for several reasons. So there are some cases where you might have better bias than functional maps provide you. Like, for instance, if you know that your maps are conformal, there are some very nice representations for conformal correspondences that either rely on local cross parametrization or even mapping to different domains. That, I don't know, there's some very nice work by Jeroen Lippmann, for example, and his colleagues. And in those cases, they basically can get continuous correspondences much like efficiently. So if you have some stronger bias on the nature of correspondences that you want, definitely, I think other maybe paradigms could be more useful. There is something interesting that maybe so for another limitation is Laplacian basis, right? So Laplacian basis could itself be limiting because, for instance, if you don't have, like, if you have noisy data or if you have partial correspondence, if you have scenes, for instance, Laplacian basis is not very appropriate. So I don't think that in that case it's definitely not the best framework. But there's something that I found interesting. Like in this last project I mentioned in our NeurIPS paper. So there are two components to functional maps. There's basically the embedding component. So for every point you find some kind of a coordinate set, and then the functional map framework is typically basically the values of the eigenfunctions at that particular point, right? But you can also do the same with general functions. It doesn't have to be Laplacian eigenfunctions, right? So you basically find some embedding into some space. And what's interesting is, like in the functional kind of map framework, you also ask for rotation, a linear transformation across these embeddings, right? And what kind of was interesting for me is that in that kind of project, like typically what people do is, if you're trying to find correspondences, you can just map to some feature space and say, okay, find features such that nearby points have, basically similar points have nearby features, right? And that's, very standard. So just a feature learning approach. Now, what was interesting to me in that project was that leaving this extra degree of freedom of linear transformation, even without the Laplacian basis, actually seemed to help in the training. So it somehow regularized the problem. Basically, instead of finding a canonical embedding where two shapes have to have the same exact coordinates, like the corresponding points have to be mapped to the same locations, leaving this extra linear transformation degree of freedom somehow helped to get more robust and more easily generalizable results. So I think there's something there. Honestly, I don't fully understand why that is. I think there's some kind of extra degree of continuity that you get through this linear transformation. So I really feel like it's worth investigating. So maybe that could be some, a little bit extra work in the future, going beyond the Laplacian basis, of course.
Max, I have another question. I really like the idea that you are advocating unsupervised approaches, which do not require any supervision, because that obviously is more elegant and is able to generalize to other classes of shapes, etc. And as you said, this is difficult when you tackle challenges where you have less isometric transformations, etc. But I think one remedy to this problem might be to look into, rather than pairwise matchings that you've been talking about in your presentation, to consider collections of shapes and consider multi-matching. Have you looked into that at all?
Yeah, you're right. It's a very strong signal. And so this like cycle consistency in a collection, for instance, is a very powerful tool. Yeah, in or having this multi-way matching, you get lots of regularization this way. We tried some basic things. So I have for non-learning based approaches, I have a couple of papers of doing this collection consistent mappings and collections where you can get better results, especially for non-isometric shapes. In the context of learning unsupervised methods, we tried doing triplets. So instead of doing pairs, doing triplets and measuring some, cycle consistency in triplets. It seemed it didn't strongly improve the results, but I think there's something else. Like I definitely think it's a good idea, and we need to dig deeper, and then maybe it's more to be done for sure. So we tried basic things. I think it's not full story yet.
Yeah. Thank you.
There's also a question from the YouTube chat. I mean, it's just a general question, of course, because people on YouTube did not see your talk. I will just read the question. Okay. Could you talk a bit more on inverse spectral geometry, as well as the current limitations and future developments on shape analysis?
Wow, great question. Well, luckily we're organizing a tutorial on inverse spectral geometry at Geography, so it'll be a good opportunity to talk about this. So I would say that, okay, so inverse spectral geometry, I mean, for those not familiar, is this problem of how much shape information you can recover from spectral quantities like Laplacian eigenvalues. It's the most standard example. And there is this famous math problem of, can you hear the shape of the drum? And yeah, we've been working, especially collaborating with Emanuele Rotola and some of his students on trying to synthesize geometry, first without learning and more recently with learning techniques based on these spectral quantities. And so I think, I treat this direction as we're basically providing some empirical evidence that, interestingly, so there are some counterexamples to you cannot hear the shape of the drum in general. So it's impossible to recover the geometry from the Laplacian eigenvalues. But it seems that in practice, you actually often can. So, with kind of strong regularization and with a little bit of learning, you can often recover good, like quite accurate, surprisingly to me, surprisingly accurate reconstructions just from the spectral quantities. I think that, so there was a lot of activity in pure math and like applied math communities. And now I think there's an interesting kind of opportunity also from shape analysis and learning generative models. So we're just investigating this. There's lots of questions that we don't know. For example, what happens in the case of partial shapes, or, if I give you can you predict, for example, like how do you stitch together shapes or from the Laplacian? Even understanding when exactly this problem is solvable, I think we're still not quite there yet. But what is also interesting is that the spectral, just maybe as a small comment, Laplacian eigenvalues basically provide a kind of a latent representation for a shape. And it seems to be complementary to like latent vectors that you typically learn from, standards, let's say autoencoder networks. So it seems like you could maybe even combine the strengths of, like, let's say Laplacian eigenvalues as one latent representation and latent like feature vectors from autoencoders. The second question was about the challenges of shape analysis. I guess the big challenge I would say right now is making things robust. And I know that lots of you guys and Daniel, your students and colleagues have worked very hard to make some of the geometric algorithms applicable to real data. I think for some things like shape correspondence, we're getting there, but maybe not quite there yet. So really tackling this problem head on, like dealing with real noise artifacts, dealing with partiality in a strong way, changes in mesh structure, all of these problems that you see I think, you know, it's an important task, and now we're getting the tools to do it, but I think I mean, it's kind of more a little bit in the future. It still requires some work. So that would be my answer.
Are there any more questions?
Maybe I have one question. So Max, I really like your work on this geometric deep learning, and I also like your work on this SURF-MNet, so which is basically unsupervised approach. But the geometric deep learning is a supervised approach.
Yes.
It seems like the supervised approach, the unsupervised approach from this SURF-MNet, the loss is quite general. So have you tried to apply this unsupervised loss to this geometric deep learning and to see how it generalizes?
Yeah, that's a great question. Actually, we have, and I even have a backup slide for this. This is basically exactly, I think, your question. So there's a paper we had at NeurIPS last year. It's called Weakly Supervised Deep Functional Maps. And the general idea was exactly this, so to take this unsupervised losses and try to apply them in the context of like this deep geometric deep learning, okay? The thing is that you have to be a little bit careful. So, and it took us some time to understand this. So you have to be careful, especially with respect to symmetries. Let's say I give you, you know, two human shapes, and one is, you know, rotated one way and the other one is rotated another way. It's often very difficult, especially for intrinsic approaches, to distinguish left and right. Okay, so you can often get mapped, you know, left to right and right to left. So you need to add this information in there somewhere, right? Because if it's fully unsupervised and intrinsic, and you don't encode orientation, you cannot distinguish left and right, okay? So this is where the weakly supervised comes in. So basically in this paper, we assume that the input shapes are roughly aligned in space. So you can be in totally different poses, but at least the left should be approximately on the left-hand side of the space, and the right, you know, I mean, it's very loose. So these are the kind of images that we have. I mean, it's not very restrictive, I think. But basically, if you have this kind of data that's weakly supervised, so just rotated in space, so it's basically like rigid supervision or approximately rigid supervision for non-rigid matching, okay? And that seems to be enough to get good results, okay? So if you can pre-align at least approximately, and then you can extract features from the geometry and use unsupervised training, and you can get, you know, good correspondences this way. You have to, like, if you don't do it, it seems difficult. I mean, you have to inject orientation information somewhere, and I would be very dubious of any paper that claims to avoid this, you know, because that information has to come in from somewhere, right? And it, you know, so you don't want to do overfitting.
Thank you.
Thank you.
More questions?
I have one general question, maybe. In view of all these new implicit representations using deep neural networks, do you see one way or the other where we could converge the spectral methods with the implicit methods?
Yeah, it's a great question, and actually, this is something that, you know, we've been looking at. I feel it's a little bit not trivial because, you know, even with implicit methods, constructing good like autoregressive models is not easy. I mean, like, for example, this deep SDF, I mean, it's like this decoder only approach is tough because it's not an actual representation, right? So there's some like test time fitting. I mean, there's some follow-up methods that try to address this, but I think this implicit surface representation is very powerful for, you know, basically constructing high quality like generative models. But for shape analysis and shape processing, in my mind, it hasn't yet shown its full potential. And I think, you know, we need to address some questions first, like how to, you know, build good, you know, maybe autoregressive or some models that allow us to represent shapes with the ultimate goal of reconstructing implicit functions. So I think it's definitely possible. So like it's a very powerful generative model. So we want to use it for shape analysis and like shape correspondence as well, of course. But I think it requires answering some questions that we still, at least I don't know how to answer very well. But I definitely think it's a great direction. So I'm like definitely excited to work in this area. So, yeah.
More questions?
I have one or two. Thank you, Max, for the nice talk. I was wondering, you mentioned that learned diffusion is robust towards the choice of the discretization of the mesh.
Mm-hmm.
And I think gauge equivariant neural networks from Maurice Weiler and so on, I think they also try to achieve that. But would you say that learned diffusion is better because it kind of discretizes later? It's kind of a more continuous philosophy or something like that?
Well, that would be my, yes, that's in my experience exactly that, because I think in some sense, I mean, they're doing a very like related, they're trying to solve a very related task for sure. But I think that learned diffusion, I mean, what is the big advantage of learned diffusion is that we can kind of use the all of the research that's been done on how to make robust diffusion, you know, on general domains, and we just benefit from that directly. And as far as I know, diffusion is one of those things that is probably one of the best studied, you know, PDEs, and one of the most robust things that you can, you know, simulate, especially for like not, you know, extremely tiny time. But other than that, it seems, you know, just extremely robust in general, in my experience. Yeah. It's also very simple. I mean, like really in terms of speed, it's a very big advantage.
Okay, thank you.
Thank you. I mean, that's my view, at least. Yeah, really biased today. Yeah.
Do you have a second question, Vladimir, or was that the question?
If time permits, I would be curious about the slide that Max skipped early on. There was something about equivariance, maybe slide 10 or something like that.
Yes. Well, I skipped it in the sense that I would be happy to go through the notation and the calculation, but I didn't want to like bore everyone, especially early on. But I think this is it, right? Is this it or?
Yes, yes.
The point is, you know, how do you compute equivariant convolution of signals on surfaces, right, without relying on a particular canonical direction tangent plane? That's the goal that we tried to solve in this paper. And the general idea is that, okay, if I have a directional function, so a function that depends on a pair of, so on both a point and a tangent direction in the tangent plane of that point, first you can pull back that function onto the tangent plane of x. So let's say I give you a point x, then for any point p in this tangent plane, I first find its like corresponding point through the exponential map. And I can also find the corresponding tangent direction through the parallel transport, okay? And so that gives me basically the exponential map. So then I can borrow the value of this directional function. So this gives me a real valued function in the tangent plane, okay? So what did I just do? I took a directional function on the surface and pulled it back as a real valued function on the tangent plane, okay? And once I have that, then I can take the kernel, right, which is a real valued kernel, and I can apply, basically I just take a dot product between this kernel, like any rotation of this kernel, right? So for every rotation of the kernel, I get a single value, and that gives me a scalar, right, per direction in the tangent plane, okay? And so, and you can basically prove that this is equivariant. So that's all. That's the main construction, right? And you can stack these, you know, signals.
No dependence on the chart?
There isn't dependence on the chart in the sense that there's no, like, we never use a canonical direction, right? It depends on the, like, up to the injectivity radius, like if you can, you know, like if you don't go beyond the, like where you can parameterize, there's no dependence. Of course, at certain, if the patch is too large, then there's, you know, you might run into trouble. That's it.
Okay, thank you. That's cool.
Sure.
All right. Thank you again, Max, for your very nice talk and also for the great and exciting Q&A session. I think this concludes our lecture for today.